Alright, so we're going to talk through our group work on vectors. And the first problem is about vectors between stuff. Asks us to draw the vector that starts at the point 2, minus 1, 0 and ends at 2, 3, 0. So we can quickly sketch that in. So 2 in the x, and then minus 1 in the y brings us over here, and 0. So there's our first point. Ends at 2, 3, 1, so the same x coordinate. And then 3 in the y, something like that. And then 1, I'll come up to exaggerate, in the z direction. There's our second point. And we're looking to draw the vector that starts here on the left and ends at our point on the right. So in order to write the component form of our vector, we need to know how our vector is changing in the x, in the y, and in the z. Notice as it moves from the first point to the second, the x coordinate doesn't change at all. It's just 2 the entire way. So the change in x is actually 0. The y, though, it moves from -1 over here on the left all the way up to 3 on the right. So that's a change of +4. From the start to the finish. And then the z starts at 0 and ends at 1, and so that's a change of +1. So those are our components for our vector here in blue. All right, second part asks us to think about how we constructed this specific vector to get a general formula of the vector r that stretches from first point, here are its general coordinates, to the second point. And so again, this vector is going to have 3 components, and we just need to figure out the change in x, change in y, change in z. And so here, if we kind of look back at our original specific vector that we formed, the way we could find the change in x is by, one way to see it is by looking at the coordinates. Our x coordinate doesn't change, whereas moving from the first y to the second, right, bumps up by 4. And the way that we can find that difference of 4 is taking the 3 minus the -1. Right, and similarly, the change of 0 that we saw on the x, we could see by 2 minus 2, giving us 0. And similarly, our change in z we could see by taking this 1 in our second point, subtracting the 0 from our first point. And so this is kind of giving us the thought, oh, well, to get the change in our different coordinates, we can just subtract them. So take the x coordinate from our second point, subtract the x from our first, and similarly for our y and z components here, taking the coordinate from our second point and subtracting the coordinate from our first point. And so this is a nice general formula that we can use as a way to slap down the vector that stretches from one point to another whenever we come across that. All right, moving on down, we're wanting to find a vector that has the same direction as this vector, but has length 6. So there's some different ways to think about this. But, one way that I like to use is to think of this in 2 steps. So this vector here, we can think of as having, whatever length it has. And step 1 is, well, maybe it's unclear how to make it length 6, but we can make it maybe length 1 if we scale this by what we need to get a unit vector. So make this thing a unit vector right here on the picture here. This would look like this. So we're just scaling it so it has length 1. And then step 2 is take that unit vector and stretch it up by 6. And once we have a unit vector length 1, we can just stretch by 6 in order to get a vector of length 6. And so here, well, here we have our vector, -2, 4, 2. Well, what's going to be the unit vector in that thing's direction, well, what we got to do is just scale that vector by its size. All right, and so let me just give this vector the name v. All right, so the size of v, using our formula, generalized Pythagorean theorem going on, is square root -2 squared plus 4 squared plus 2 squared, which is root 4 plus 16 plus 4, which is root 24. Okay. And so here, the unit vector that we are trying to get our hands on is then the vector -2, 4, 2, scaled by its size, root 24. This vector has length 1, and so if we want to get that length scaled up to a length of 6, we just need to scale this vector here by 6. And so our final answer, if we do that and maybe just pull out our scalars to the front, is 6 over root 24 times our original vector. So there's our vector that we're looking for. If we wanted to, we could distribute that scaling to each of our 3 components, but I'll just leave it out front. Moving down. Here we have a setup here with some labeled vectors, and we're wanting to express, in this case, D in terms of A and B. And this one actually has a number of different ways that you could go about it. One way that I think is a nice way to think about getting our hands on D is that D is half of the vector, notice stretching from Q to R. Maybe I'll draw that in green. So here's a vector in green stretching from Q to R. Right, D has that same direction, but there's 2 little bars here indicating that the length of this vector D is just half of this green vector. And so, well, if we can get our hands on a way to write our green vector, well, then we can just scale it by 1/2, and that will hand us D. But here's the thing. Our green vector stretches from the tip of the vector A to the tip of the vector B. And so because of how vector subtraction works, right, we always have the endpoint and then subtracting the starting point. Right, so this vector in green ends at the tip of B, so this will be B minus A. So our green vector. This will stretch from the tip of A to the tip of B, as our green vector here does. And so, as we said earlier, that means that D is 1/2 that green vector. So we'll just scale it by 1/2. And we could leave it like that, or if we wanted to, we could distribute that 1/2 across. All right, next let's express C in terms of A and B. Again, there's some different ways to think about this. One possibility is that if you notice that the endpoint of C, right here in the middle, we could get by first doing A, and then if we slide D over and do that here, that will end us at the tip of C. And thinking about how vector addition works, that means that C equals A plus D. Right, you start at the start and point to the finish after lining the vectors up in a row. And so here we're asked to express C in terms of A and B. Here we have A and D. We just need to break up this D as we did earlier using one of these two forms. Maybe I'll just use the one I started with here. So this is A plus 1/2 B minus A. Moving on down. Here we just have some computation fun. So here we have a couple vectors A and B given in IJK notation. We're asked to find this vector here and the size of this vector over here. So here to start, it's not necessary, but I like to immediately write these vectors in component form. So 2 minus 4, 4 is A, and then B. Notice there's no I going on, so that means the X component is 0, then 2 for the Y, and minus 1 for the Z. All right, and so 2A minus 3B. Well, for 2A, we're going to scalar multiply our vector A here by 2. That'll double all of the entries. So it'll be 4, negative 8, 8. And scaling the B by 3, we'll triple all those. So 0, 6, negative 3. We're subtracting those, and so we do that component-wise. All right, so doing our X components, 4 minus 0 gives us 4, and then 8 minus 6, and excuse me, negative 8 minus 6 is going to give us negative 14. And then 8 minus negative 3 is going to be 8 plus 3, so 11. Then the size of B minus A. First, we've got to find B minus A. That's the size of 2 minus 1. We're subtracting A to negative 4, 4. So component-wise again, the vector we're taking the size of is 0 minus 2, 2 minus negative 4, so that's 6, 1 minus 4, sorry, negative 1 minus 4, which will be negative 5. And we're taking the size of that vector. So here we have our generalized Pythagorean theorem going on. And so negative 2 squared plus 6 squared plus negative 5 squared. So what do we get? Root 4 plus 36 plus 25. So 40 plus 25, so 65, root 65. So that's the vector and the size that we get from those two computations. All right, moving to our last problem here. We're finding the unit vectors that are parallel to the tangent line to the curve y equals 2 sine x at the point pi over 6, 1. This is an interesting one. I like this one. So the idea here is we have our curve 2 sine x. It's going to look relatively like a sine, just a stretched sine graph. And pi over 6, 1 is going to give us a point. This is pi over 2. So pi over 6, it's going to be like here. Right, and so we can imagine the tangent line to our graph, and we're wanting to know the unit vectors that are parallel to this tangent line. And right away, we can at least get a sense of how many there are going to be. Right, there are going to be 2. All right, there's going to be 1 in this direction, and then another vector pointing in the opposite direction. All right, so we should have 2 vectors at the end of the day. Well, in order to start getting a hold of these vectors, it's going to be useful to figure out that the slope of this tangent line. Now that's really going to be what allows us to get a hold of the components of these vectors. All right, so if we want to know the slope of our tangent line, then we should look at the derivative. All right, so y prime here is 2 cosine x, and so y prime at pi over 6 is 2 cosine pi over 6, which, remembering our trig, is 2 times root 3 over 2. The 2's cancel off, and we're just left with root 3. All right, so this root 3, remember, this is our slope of our tangent line. And so there's different ways to go from this information to get our vector. I'll kind of get there in 2 steps. The first is I'm going to get a vector that just has the right sort of slope here, that's in line with our tangent line. It's parallel to it. And then I'm going to scale it so that it is a unit vector. All right, so to get one that's kind of in line, we can think about what this slope means, right? Slope is rise over run, and root 3, if we want, we could think of as telling us root 3 over 1, right? Or in other words, well, if we move in the x 1 unit, then we're going to move up in the y root 3. Right, and this is analogous to, say, if our slope was 7 to our line, well then if we ran 1 in the x, then we'd rise 7 in the y. And so right here, we can see from our picture, oh, the change in x and change in y that we'd have. And so we can write down the component form of this blue vector here. So our blue vector, in the change in x, we can have 1. Change in y, we'll have root 3. All right, but this is not a unit vector. We need to scale it so that it is. And so now we need to know the size of our blue vector, using, in this case, just essentially Pythagorean theorem. We'll get 1 squared plus root 3 squared, which is root 1 plus 3, which is root 4, which is 2. All right, and so we can now take our blue vector and scale it to get our unit vector. It'll be 1/2 times our vector. And that'll be this one here in the same direction as that blue vector. Notice to get our other unit vector, we just need to flip the direction, and we can do that by scaling this by a -1. And so if we want, we can just say, hey, our 2 unit vectors are plus and minus this vector right here. That's it for today. See you next time.